Hello, I'm Mirdad Simkani, your calculus professor, and this lesson is about Riemann sums and how to approximate areas between graphs of functions and the x-axis. So let's look at some figures. So here we have a function, and we want to estimate the area between its graph and the x-axis from some x value to another x value. The easiest way to approximate areas is by rectangles, because rectangles are easy to compute. The area of a rectangle is the height times the width. And if we make these rectangles smaller, you can fill the gaps better. So the more rectangles we choose, or the more rectangles we fit in this area, the more accurate our estimation would be. Now, here, if you noticed, these rectangles are irregular. Some of them have a smaller width, some have wider width, and it's not an efficient way of computing them. If you program a calculator or a computer, you have to use different widths for these rectangles. But if you make them equal, it would be easier to compute and more efficient. So here's an example. So all of these rectangles have a common width, which we call delta x. And this delta x can be very small. And then if you notice that the way these particular rectangles are fit at the midpoint between each subinterval, we have to evaluate the function to get the height. The height of the rectangle is at the midpoint of each of these subintervals. And such a method is called the midpoint sum. So we have to add all these areas, and that is the sum that we call midpoint sum. And we denote this with the capital letter M, and then how many rectangles you're using, that would be used as the subscript. In this case, there are 8 rectangles, 1, 2, 3, 4, 5, 6, 7, 8. So this is M sub 8 that we calculate. So if we have the delta x, which is just dividing the whole interval by 8, that will give us delta x. And the heights, for the heights, we need to evaluate the function at the midpoints. So we need to know where the midpoints are, the x values at the midpoints. You plug them into the formula for the function that gives you the height. You have the height, they're all called multiplied by delta x. You can factor out the delta x because they're all the same. It's just a matter of adding all the heights and then multiplying that sum by delta x. That gives you an estimation for the area. And there's always an error, there's some rectangles can go higher than the function and give you extra area, and in some parts they're below and you're losing area there. But midpoint is generally not a bad rough estimate for these kind of areas. there are more sophisticated methods. If you take a numerical analysis class, you will learn all about it. And then there are other ways to pick where we want to evaluate the function. For example, this one is called the left endpoint sum, because for each of the rectangles, the height would be the value of the function at the left endpoint. For example, here, this left, for this interval, at this left endpoint, we're evaluating the function, right? You plug this x into the value of the function to get the height. And the widths are again equal, and there are delta x. You can calculate it by dividing the total area, the total length from left to right by 8 in this case, because there are 8 rectangles. And then, of course, there is also a right endpoint sum, and that would look like this. Okay, let's put it this way. Okay, so this is the right endpoint sum, and notice that the value of the function is at the right endpoints. So if this is the base of a rectangle here, you evaluate the function at the right end, because the right upper corner is on the graph. So that's what we do. So we're doing an example right now. So here's the example. Suppose the above function has this formula. So this is the equation of the function f of x equals x minus 5 quantity squared, and we want to estimate the area between the graph and the x-axis. So the line at the bottom is the x-axis, like here, this is the x-axis, and we want to do it from 0 to 4. And by the way, this one, for the right sum, we call this R8, and for the left we call it L8. L for left, 8 for how many rectangles, L for 8, just like M8. M for midpoint, 8 for how many rectangles. And so for each of those pictures, we're going from 0 to 4. So let's do R8 first, from 0 to 4. So that means this each of the so because there are 8, so that means this is a half, this is 1, 1.5, 2, 2.5, 3, 3.5, and 4. So those are the places where we evaluate the function. We don't evaluate at the first one as 0, because that is not on the graph. We evaluate the function at half, at 1, and all the way to 4. And delta x in these problems, delta x is the length of the interval. So I'm going to make a formula here. Let's call the left endpoint A, the right endpoint B. So this is in general. So the length of the interval would be B minus A. But then you divide it by n. N is the number of rectangles. N is the number of rectangles. And in this case, we have 4 minus 0 divided by 8. And that's how we get half. So now we have the width of each rectangle, and we can calculate their heights and then add all the values. So to make a space for this one, let me push this down. All right. So the area is approximately, because it doesn't exactly fit the curve. And by the way, because the function is decreasing, when you do a right sum, it will always underestimate the actual area. And for a decreasing function, the left sum overestimates. So let's try this. So it's delta x, which is so delta x in this case is half. Each of the widths is half. So I'm factoring that out. I'm just adding the heights. And the function, I'm going to write the formula for it. So the y is x minus 5 quantity squared. So to estimate that, let me put it here so it fits in one slide. Okay. So you evaluate this function at each of the points that hit the corner, hit the graph, at each endpoint that hits the graph. You see, on all these are the heights. You evaluate the function at, let me write it in general, okay, so, and then we plug them in. So here's a general formula, delta x, you evaluate f at, let's say, x1. In this case, this would be x1, this is x2, x3, x4, x5, x6, x7, x8, and the one on the left is x0. So you can label them from x0 to x8. For the right sum, we skip x0, so we go from x1 all the way to x8, or xn in general. So we are adding these function values. I'm going to use ellipsis, so we go all the way to f of x8. So it's just a simple arithmetic, 0.5. Now f of x1 is to put 0.5 in here, so that's the formula. 0.5 minus 5 is minus 4.5, and you're squaring it, so that would be 4.5 squared plus the next you put in 1 minus 5 is 4, so you have 4 squared, and then you plug in 1.5, and that gives you 3.5 squared, and similarly get 3 squared, because you change x by halves. So, and then but you're subtracting 5 from it, so these numbers go down, and you can see the heights are going down. So the next would be 2.5 squared and then 2 squared, and then 1.5 squared, and the last one, which is 4 minus 5 is 1, so the last one is 1 squared, which is just 1. And then you figure whatever that is, okay? So it's not big deal, you just put in a calculator. So there's not a point. The point is not to get a number, the point is to understand the process. So that's a right sum. Now we're going to do a left sum here. So these two we can so still the function is the same, so we have delta delta x still 0.5, so the interval is from 0 to 4, so we're evaluating the function at x0 and so on. So this is x0, x1, x2 all the way to x8, but we don't use x8 for the left sum. So for the left sum, the area is approximately delta x times the value of the function at x0. You start from the first node, the left node or the left endpoint x0, but you don't include the right endpoint. F of x0, f of x1, and finally f of x7 rather than x8. So you don't include x8. So these are where you evaluate the functions on the left. And then you put the values in here, 0.5, f of x0, that was 0, and then this would be 0.5, 1, and so on. So you get the function f of x is x minus 5 quantity squared. So when you plug in 0 for x0, so this is the x0 is 0, x1 is half, and so on. x7 is 3.5. So the last one you plug in is 3.5, and the first one you plug in is 0. So when you plug in 0, you get minus 5 squared, which is the same as positive 5 squared. And then you plug in half, that would be 4.5 squared, and then 4 squared, 3.5 squared, 3 squared, plus 2.5 squared, plus 2 squared, plus 1.5 squared, and you stop. You stop at plugging in 3.5, and then whatever that gives you is the left sum. By the way, you can call, let's just use the notation we normally use. We call this one L8 and this one R8. Again, 8 refers to how many rectangles you're adding. For the midpoint, you have to, so knowing this goes from 0 to 4, and each subinterval has width half, So the first midpoint, this one, is 0.25. The next one is 0.75. So again, delta x is half. Okay, so the midpoint is 0.25 away from an endpoint. So the endpoints are at 0, half, 1, 1.5, and so on, but the midpoints are halfway between these nodes. And the next one would be 1.25, and then the next one is 1.75. You know, 1.75 would be the next one, and then they increment by half. So you keep adding half to each of these x's where you're evaluating the function. The next one would be 2.25, and the next 2.75, and the next 3.25, and finally 3.75. So those are the places where you evaluate the function. So in this case, m sub 8 is equal to, which approximates the area. So the area is approximately equal m sub 8, and m sub 8 is delta x times f of 0.25 plus f of 0.75 plus f of 1.25, and so on, plus f of 3.25 plus f of 3.75, and then you stop. And that's what we do. And f of x, I'm going to write it here. F of x is still x minus 5 squared. It's the same function. So m sub 8 is delta x is half, just like before. And then f of 0.25, when you plug in 0.25 here, you subtract it from 5 and you square it. So this is 4.75 squared. The next one, you evaluate f at 0.75 and you're subtracting 5. So the previous value where the previous base 4.75 and now is 4.25. It's half a unit less because delta x is half, so you add half to x each time. When you add half to x, you're subtracting half more from 5, right? Or you're subtracting half from your previous amount. So the next amount would be 3.75, but you have to square it because the function requires it. And then the next would be 3.25 squared, and then 2.75 squared. Make sure you add 8. 1, 2, 3, 4, 5 plus, I'm going to continue here, 2.25. You know, the last place you evaluate the function is 3.75. And when you subtract from 5, you get 1.25. So this is squared, 2.25 squared, plus half less, 1.25 1.75 squared, and now half less, 1.25 squared, and then whatever that gives you. So this is the midpoint sum. If you have the formula for the function and you know how many areas you're adding, how many rectangles you're adding, and where you're evaluating the function to get the heights, whether it's a midpoint or left endpoint or the right endpoint. So all of these problems work the same way. Sometimes you have the picture is given, sometimes you only have the equation of the function that you're dealing with. So this concludes the lesson on approximating areas between the graph of a function and the x-axis.